All right, in our introductory lecture on momentum, it hopefully seemed fairly easy. There was basically one main equation for momentum that we needed to know, and that was momentum equals mass times velocity. What makes this unit maybe a little more challenging is when we start dealing with collisions. So we have one item and it collides with another item, and then maybe one item stops and the other one starts going, or they both continue to go, or they go off at angles or whatever. When we're dealing with collisions, we have to do what we call conservation of momentum equations. And really all that's using is this equation. And what it's basically saying is that the momentum before a collision of all the parts, let's say that there's two things. Let's say there's a ball rolling and it's going to hit another ball. It's going to collide with another ball. So what the conservation of momentum says is that the momentum, or the mass of the ball, mass of the first ball times the velocity of the first ball, plus the mass of the second ball times the velocity of the second ball, all before the collision. So all of this stuff is all before a collision occurs, that the total momentum before a collision will equal the total momentum after the collision. So I'd again have m1 v1 plus m2 v2, but this though would be after the collision. So you always, when you look at a problem, you need to figure out at what point is the collision happening, and calculate all the momentums of every object before and all the momentums of all the objects after, and they need to be equal. And this is how we can figure out, like, for instance, what the velocity of one of the objects is after the collision. If you're given all the other information, you can apply the conservation of momentum and be able to figure things out. So the key with this is that in any type of collision, we're going to have two types of collisions. So there's some kind of definitions we need to talk about here. We have what's called elastic collisions, and we have inelastic collisions. These are the only two types, elastic and inelastic. Basically, everything is inelastic collisions. Almost everything is inelastic collisions in reality, in our problems. What it basically means is that momentum is conserved, which means this right here: the momentum before a collision and after the collision will always be equal. So the momentum is conserved in any type of collision. So momentum is conserved here, momentum is conserved here. So what's the difference between elastic and inelastic if momentum is conserved in both collisions? The key is that the kinetic energy is not conserved in inelastic collisions. So kinetic energy, we can do kinetic energy conservations also. And inelastic, kinetic energy is not conserved. Not conserved. But in elastic collisions, which are basically almost kind of make-believe, kinetic energy is also conserved. And what that means is that you could do, instead of momentum being conserved like this up here, you could do 1/2 m1 v1 squared. So the kinetic energy of a ball before the collision, like the kinetic energy of this ball here before the collision, plus 1/2 m2 v2 squared, the kinetic energy of this ball here before the collision, that would equal the total kinetic energy after the collision, m2 v2 squared. That this energy before, all the kinetic energy before, would equal all the kinetic energy after. This would say that the kinetic energy is conserved, but that only happens in elastic collisions. And basically, that's never, except for like on the atomic level. When we're talking about the atomic level, when we have atoms colliding with each other in kinetic theory, we do assume that those collisions are pretty much elastic. So what that means is not only is the momentum conserved, the kinetic energy is also conserved as well. So momentum is always conserved. So in all of our problems we're going to do, you can always have the momentum be conserved. But only in elastic collisions can you also say the kinetic energy is conserved, and you have another equation to work with to try to figure some things out. So that's going to be an important thing going forward here, and we do some problems. You might need to know in certain situations if it's elastic or if it's inelastic to be able to figure out some things. Okay, we're going to do 3 problems here in this lecture, 5, 16, 17, and 18 if you have your books and you want to get the checkoffs complete. These problems are pretty, they're a little easier than what we're going to be doing a little bit later. Remember, momentum is vectors. Momentum is vectors. So these 3 problems are going to be just dealing with things that are colliding left and right, just in one dimension. So they're not going off at angles. So if they're going off at angles, that makes the problems harder because you're doing like real big vector problems. If they're not going off at angles, like they're going left and right, then those are easy vectors to add together because you just literally add them and subtract them, right? If you have a vector going to the right of 3 and then a vector going back to the left of 2, that ends up being a vector of 1 to the right. So those are easy to add because you literally add and subtract them together. And so that's what we're going to be doing in these first kind of 3 problems. So if you look at this first problem, it says there's a 50-kilogram skater and a 70-kilogram skater. I don't know, ice skating, roller skating, whatever they're doing. And they're just standing there, and they push off of each other. So if we draw this, we got skaters, and they're like something like, oh boy, I made that person with really short legs. Like this, and they're going to push off of each other. This is a 50-kilogram skater, and this is a 70-kilogram skater. And they're going to push off of each other, so they're obviously going to be going in opposite directions. If the lighter skater moves off at a velocity of 4 meters per second, so we do it this way, and this will be 4 meters per second vector. What is the velocity of the other skater? So we're trying to figure out what is the velocity of this skater. And the way we do these problems is conservation of momentum. We do everything pretty much the same way. Conservation of momentum. So we need to figure out the momentum of both the skaters before the collision, and then we need to equal that to the momentum of both the skaters after the collision. So if we do that, we'll call this skater 1. This is skater 2. So what's the momentum of the skater 1 before the collision? What is the collision, by the way? The collision is actually, in this situation, when they push off of each other. That's technically that would be the collision aspect of it. So there's momentums before, and then there's an event. And the event here is pushing off of each other, and then we figure out what are the momentums after that event. So before the event, we have the mass or the momentum, of skater 1, and that would be let's just write it out. M1 times V1, right? That's before, plus the momentum of skater 2 would be M2 V2. Okay, how fast that skater is going times its mass. And then that should be equal to the mass of the skater afterwards times the velocity of the skater afterwards, plus the mass of the skater afterwards times the velocity of the skater afterwards for the next one. Okay, so I could kind of do this. This is skater 1, and this is skater 2, and this is skater 1, and this is skater 2, and this is skater 1 before, and after. So I don't know. I'm just making sure that you kind of get that all in your brain. I think after you do several of these problems, it kind of gets obvious and it's pretty easy to do. So momentum problems, a lot of times students are pretty successful with these. So hopefully this will be a good thing to teach online. Okay, so what's the mass of the skater before skater 1? It's 50. And how fast is skater 1 going before the collision? He's not moving at all. So 0. Skater 2, before the collision, the mass is 70. And how fast is skater 2 going before they push off of each other? He's not either, 0. Okay, so after the collision, what do we have? Well, we have the mass of skater 1 is 50. And the velocity of skater 1 is 4. Okay, that's a plus 4. That's what it says, 4. Okay, plus What's the mass of skater 2 after? Is 70. What's the velocity of skater 2 afterwards? We don't know. We're going to put in v. That's what we're trying to solve for. Okay, so on the left side, we have 50 times 0 is 0, plus 70 times 0 is 0. So on the left side, we actually have 0. So we have no momentum at all before the collision. No momentum. The total momentum of the whole system is 0 before the collision. What is it afterwards? Well, 50 times 4 is 200, plus 70 times v is 70v. And we're trying to solve for v. So what are we going to do? We're going to take the 200 to the other side, and that'll be a negative 200. And that'll equal 70v. So how do we get v? V is negative 200 divided by 70. And if we look in the calculator here, 200 divided by negative 70 would be a negative, basically 2.9 meters per second. So this skater here is going to go at a negative 2.9 meters per second. Why negative? Because momentum is and velocities are vectors. They're vectors, right? So if we designated this skater going this way and we designated it as 4, we designated it positive, we know that this skater is going to go the opposite way. Now, I hope that doesn't confuse you. I turned it around. Normally to the right is positive and to the left is negative, but I didn't designate it that way. So this one's going plus 4. This other skater has to have a opposite velocity, a negative 2.9 velocity. Okay. I hope that makes sense. It's really difficult to teach this without you asking questions and me looking at your very confused faces, so I know I need to do it over again. So you can watch this again and hopefully maybe figure it out. Okay, let's go to another problem. We have a 6,000 kilogram car moving at 20 meters per second. Okay, so we got a little car here, 6,000 kilograms. It's moving along at 20 meters per second. Okay, it crashes into a 4,000 kilogram car. So here's a 4,000 kilogram car that's at rest. Okay, so right now this is at 0 meters per second. This is before the collision, and they stick together. Okay, they stick together. When they crash, they actually stick together. What will be their new combined velocity? What will be their new combined velocity? So after this, so this is before, right? Okay, after it's a big messy car mass. Okay, and what is the velocity afterwards of this car? Well, what would the mass of the car system be afterwards? Now they're one big object, right? And it would have a mass of 10,000 kilograms. Mass of 10,000 kilograms. So we need to figure out what is v. So the momentum before the collision is 6,000 times 20 plus 4,000 times 0. And then afterwards, after the collision, it would be 10,000 times v. Okay, so 6,000 times 20 is 120,000 plus 0 is still 120,000. That needs to equal 10,000 times v. So what is v? V would be 120,000 divided by 10,000. We can cross off zeros. That's 4 zeros. 1, 2, 3, 4. Okay, and 12 divided by 1 is 12, right? So 12 meters per second is how fast that car system is going to be moving. Okay, so so we're going to do the same kind of situation. We have a 6,000 kilogram car, moving at 20, and we have the 4,000 kilogram car moving at 0. That's before the collision. After the collision, the 6,000 kilogram car moves at 8 meters per second. This time they're not going to stick together. Okay, so I have the 4,000 kilogram car is going to be moving how fast is what they're saying there. Okay, how fast? Now, actually, the question here is actually asking how much kinetic energy is lost. Okay, this is in an inelastic collision, and so kinetic energy is going to be lost. It's not going to be conserved, and we're actually trying to figure out how much is lost. So before we can do that, though, we actually do have to use conservation of momentum and figure out what this velocity is over here. So again, we had 120,000 total before, and afterwards we had 6,000 times 8. 6,000 times 8 would be 48,000 plus 4,000 V. So 120,000 minus 48,000 is 72,000, and that would equal 4,000 V. So 72,000 divided by 4,000. The velocity of this car right over here should be about 18 meters per second. So that's kind of like the second problem we just did a little while ago. Okay, so this velocity of this car is 18 meters per second. All right, so now the question actually, though, was how much kinetic energy is lost. You did have to do this first. You had to use conservation of momentum. We always have to use conservation of momentum first and figure out what the velocity is that we're looking for. But now I can say, okay, how much kinetic energy was lost? What was the kinetic energy before the collision? Well, it would have been 1/2 times the mass of 6,000 times the velocity of 20 squared, 1/2 mv squared. And the second car is going to be 0 because it has 0 velocity, so I don't have to actually calculate that out. The kinetic energy of this car is going to be 0 at the beginning. So that should equal the kinetic energy of both the cars afterwards. So afterwards you have 1/2 6,000 times 8 squared plus 1/2 times 4,000 times 18 squared. Okay, I made a mistake. This is inelastic, right? So this is not going to be equal, right? It's not going to be equal. In fact, this is going to be greater than the kinetic energy afterwards. We are going to lose our kinetic energy. If there's two ways we lose it. Basically, the kinetic energy it's lost through heat because of friction. It's also lost in like permanent distortion or damage of the cars and stuff. That all takes energy to do that, and so we lose it through that method. So the energy before a collision is always going to be more than what it is going to be afterwards. So we need to figure out the energy before the collision. It'd be 0.5 times 6,000 times 20 squared, and that's a lot. 1,200,000 joules of energy is how much it is before the collision. 0.5 times 6,000 times 8 squared equals, I got 192,000 for that one. What's the next one? 1/2, 0.5 times 4,000 times, and it was 18 squared equals 648,000 plus 192,000 equals a total of 840,000. Oh, the energy I lost, let's come up here. So I have 200,000 minus the total was 840,000. That's how much energy it had at the end. So we lost 360,000 joules, which would be a loss of 360 kilojoules. So we lost 360 kilojoules in this collision through friction and damage of the metal and indentation of the metal, all that kind of stuff. We lost 360 kilojoules of energy. But before I could do that problem, I did have to do the conservation of momentum right here and figure out this velocity. And then you can go on and you can do see how much energy has been lost. Okay, those three problems are, I think, fairly straightforward. They're easier because they're just moving back and forth. They're not real big vector problems with angles and stuff. I'm going to save that for the next lecture. So hopefully that'll help you do a couple more problems and get a couple more problems on the eLab done. Hopefully you're all working on this because your Jedi trial is going to be on Friday with no exceptions.